So in the next slide, we have investigated the effect of annealing on the magnetization dynamic properties of these one-dimensional nanowires. The reason for choosing the effect of annealing is that these magnetic nanostructures can be utilized, as we have already discussed in the previous slides, that they can be utilized for the spintronic applications to overcome the electronic devices. So whenever we use them for the spintronic devices, the effect of temperature can change the properties of these materials at the device level also. So if we understand the role of annealing, or the effect of annealing these magnetic nanostructures, we can overcome the device properties when we go for the miniaturization of the devices using these one-dimensional nanostructures. So this figure one shows the XRD image of the nickel nanowires. The first one shows the as deposited. Then when we go for annealing temperatures from 250, 350 degrees Celsius to 450 degrees Celsius, we see that the crystalline phase deteriorates, and it's becomes broader as we go for the annealing up to 450 degrees Celsius. So we can easily interpret that the annealing causes the deterioration of the crystalline phase of the nickel nanowires. Then we have investigated the magnetic properties as well. So you can see here from the magnetic properties that by the annealing of any magnetic material, we already know that any ferromagnetic material, if we keep on increasing the temperature, its magnetization, its magnetic properties deteriorates, and that ferromagnetic material becomes paramagnetic material. So the same thing will happen for the case of nanowires also. So you can see here that the nickel nanowires of as deposited shows the black line curvature, or the black line hysteresis loop. But when we anneal it at 250 degree, the magnetization reduces. So the straight magnetization reduces to the red one, and the saturation magnetization decreases to 250 degree. And then if we further increase the annealing temperature, my magnetization keeps on decreasing. So this is the clear indication that the magnetic properties changes drastically with the change of the annealing, and my ferromagnetic material can be converted into the paramagnetic materials as well. Here in this case, it will not convert into the paramagnetic, but for the case of nickel, when we oxidize it, or when we anneal it in the presence of air, it gets oxidized, and this nickel will be converted into the nickel oxide. So which is an anti-ferromagnetic material. So because of that anti-ferromagnetic nature, the magnetization will decrease. Similar effect of annealing can be investigated using the scanning electron microscope images as well. So the scanning electron microscopy images, it is clearly visible that when we keep on increasing the temperature, so the figure A of this figure shows the as deposited nickel wires. When we start annealing these nanowires, what will happen? You can see that the surface of these nanowires starts deteriorating. The surface becomes more roughy. So the surface gets started oxidizing. So my nanowires are becoming more hazy as compared to the as deposited nickel nanowires. So the oxidation will occur, and that causes the making my structure to be more oxidation of this structure happens at this particular point. Then the microwave properties can also be investigated. So here we can see that when we see the different annealing temperatures, what we observe that the line width as well as the resonance frequency. So the field line width, if you see for this specific 250-degree, for 350-degree, and for 450-degree, the line width has increased as compared to the black one to the blue one. So you can see that the field line width increases. So it won't be good for the spintronic application. So for the spintronic applications, our requirement should be that my line width should be as narrow. So since the line width will become smaller, it will result in the damping constant to be, Gilbert damping constant to be more smaller. So the precession will occur for a longer time. So it will take more time to precess the system. Whereas if the broadening of the line width occurs, so what will happen? The alpha will become more. So the precession will occur more slowly as compared to the, so smaller alpha will make the precession faster, and the larger alpha value will make the precession smaller. So it will take time to come to its equilibrium position. So the precession will become more. So the annealing causes the line width to become more, and it will again, as a result, it will cause the Gilbert damping constant to become more. We can also see the resonance field. So you can see for different, as a function of operational frequency, the resonance field can be observed that when we increase the annealing temperature, the resonance field also shift towards the higher frequency range. So it is becoming broader, and it is making the resonance peak of the nickel to a combination of nickel and nickel oxide. So it will become, it will go towards the higher region and broader one. So this shows the resonance field, and this shows the small change in the resonance. So this shows the line width, field line width for corresponding different materials. So what we observe, it is observed that the crystallinity of the nanowires deteriorates with the increase of annealing temperature. The saturation magnetization decreases with the increase of annealing temperature due to the oxidation of nickel nanowires, resulting in antiferromagnetic behavior of nickel oxide. So as I discussed already, so when we do the annealing, the nickel is converted into, in the air atmosphere, the nickel is converted into nickel oxide, which causes the deterioration of the magnetization. The broadening of the resonance field and line width was observed due to the rise in annealing temperature. So these are the interpretations which we obtain from annealing the magnetic nanowires and investigating the magnetization dynamics. We observe that the Gilbert damping constant becomes more when we do the annealing of these nanowires. So at the last, we have investigated various different properties. So this is not the end. We can utilize these nanostructures for different applications as well, since these nanostructures are promising materials for many novel applications, as they exhibit large aspect ratio, which makes them suitable candidate for microwave applications, spintronics, and biomedical applications, as we have already discussed. The unique physical properties are enhanced, such as their electrical properties, magnetic properties, optical properties, and mechanical properties can be more as compared to the bulk materials. Then the miniaturization of electronic devices is possible by using one-dimensional nanostructures. Apart from the magnetic materials, we can also deposit compound alloy materials as well in these one-dimensional AO templates or PCT templates. So depending upon the kind of template we are using, we can change the properties of these materials as well. So this is still a rising hot topic in the research area, and a lot of work has to be done in this area. Thank you.